So this last session is just to keep it simple at the end, to talk about advanced applications where you want to use other tools beyond Lambda and what the API gateway and what we saw today, and use the AWS Step Functions. So I'm not introducing me again. Probably most of the people was already here, but I'm part of the technical evangelist team. I'm Danilo, and you can reach me on danilop@amazon.com or on Twitter and GitHub. I'm always Danilop, so very easy to find me. So let's say that you liked what you saw today, and you start building your serverless application, you start creating your first Lambda function, and it's doing something, maybe something important, and then you start to have other functions that are coordinated with this function. Maybe they are invoked under some circumstances, and then this Lambda function will grow. Today we were talking about you can keep this under management from a development perspective, like with tools like the serverless framework or SAM. But there's lots of complexity that it's in how you really coordinate the flow of your Lambda functions. And this is actually similar to the same problem you would have if you have microservices and you have lots of microservices. You need some way to coordinate the flow, understand the business logic, how your business process are mapped in a flow that can go through different building blocks, like different Lambda function or different microservices. And probably at some point you have databases or queues that you need to interact with. And maybe you can even interact with legacy systems that maybe run on-premise, and they have a different speed both in development, and they don't have the automatic scalability that you can get in the cloud. That's lots of, this was really just the introduction for the people that was coming. So when you have lots of Lambda function and lots of moving parts, that's lots of effort that you need to spend in coordinating this. But as I like, it was summarized in reinventing our CTO keynote, in Werner Vogel's keynote. We really would like to help developers only write the business logic. And we would like, as AWS, to help cover everything that is not business logic, that is just a burden for the developers. So how can we make this simpler? That's what you need when you start to move from functions to applications. So I want my functions to run maybe in sequence, or in some point I want my functions to be executed in parallel. Maybe depending on the data that I have, I need to run different functions. So at some point I want to choose one function instead of another, instead of having a big function that can do multiple things. Maybe I want, and this is very important, to retry functions, so that if there is an error from a function, I want to have fine control on what's happening, catch the error, maybe retry a few times. I want maybe to have the equivalent of a try, catch, finally syntax that I usually have from programming languages at Lambda function level, so that I can try a function, catch the error, and finally clean the state of the resources. And maybe I don't have I don't like the 5 minutes limit of the timeout of the Lambda functions. I want to run my business process for hours. And so I need some coordination layer. And this coordination layer, to work with serverless technology, needs to scale out, because I can have 1 or thousands concurrent executions. I need to keep a state, because usually the problem when I have this distributed architecture is not just designing the flow, but keeping the state in a robust manner across different results. I want to deal with error and timeouts. And of course, this must be easy to use. Otherwise, we're just adding complexity to complexity. And if I have some execution, some complex business process, this must be auditable. So it must be easy for me to understand what is happening at any time in any business process running in a distributed architecture. That's why we introduced in 2006 AWS Step Functions. And AWS Step Function is a relatively easy service if you look at how it works, because it can help you define what we call a state machine. And if you studied computer science, it's really the state machines that you study in computer science. So it's a machine can have a state and change state. We use a JSON language that we created and we released in open source, so anybody can use it. The console will automatically take the language and visualize the flow of the state machine. And then if you execute the state machine with some input state, you can monitor the execution, see the flow where it goes, and at any step in the execution of the state machine, you can understand what is entering, what is exiting, and also have direct access to the logs of the Lambda function that was there. So this is the most basic Hello World. Hello World is the theme of the day, at least in my presentations. And this is a single state, single task state machine. I have a start and an end. So I can add a comment. Then I have to say which is the starting state, because the order of the JSON file can be different from the execution state. So I start from the state hello world. Then I have the list of states. I have only one state here, hello world. Then I have different types of state. This is a task. A task is something that I want to execute. And a task in this case is a Lambda function. And here I can use the Lambda Amazon resource name. So if you use Lambda, we give a unique identifier to any Lambda function. And it's called Lambda ARN. And actually, ARN, its Amazon resource name, is a general concept that we use across most of our services to give unique names to resources so that you can, for example, give permissions or know what's happening. So I execute this this task that is a Lambda function. And then this is an ending state because end is true. So the state machine ends and the execution ends here. And when I create a state machine, I can execute 1 or up to 1 million at the same time. This is the default limit that we give for state machine. So it's very scalable. And the maximum execution time is slightly bigger than those of Lambda functions. So we go from 5 minutes to 1 year. So you can have state machines that run for up to 1 year, and we keep the state across all the state changes. As I said, you can monitor the execution from the console, and we color where, if there are different branches, choices, or errors, you can see the flow of every execution where it goes. And then for every step, you can understand the input, the output, and have information on what is happening. We will see this live in the console in a quick demo. So each, as I said, each state can have a type, and those are the types that we support. So a task is a unit of work. Most often, this is a Lambda function, but we will see that there's also the concept of activity. That means that you can run code anywhere on an EC2 instance, in a container, outside of Amazon, something that runs in another data center. It can even be a human interaction that must approve or not a single step. So a task is a unit of work, a very generic concept. You can have a choice. A choice means that this state can have a choice and then go to different substates. Parallel, if you want to execute multiple states in parallel, like I want to do something and at the same time I want to do another task. Wait, if you need to wait for some time or for a specific time. So you can either give a duration or a specific time to wait for. Fail is a state that says it explicitly fails the current execution of the state machine. Succeed is the opposite, it's an explicitly terminating state. And pass is a state that doesn't do most, but it can be used to manipulate the input and the output of the state. For example, add or extract information from the state and change the state for the next step. So when we execute a task, so the task is probably the most important concept, the unit of work, we can have synchronous task, and this is when you use Lambda function. So this is, for example, I want to extract the metadata of the images using recognition, like we said today. I execute a Lambda function, this is a task, and this is my ARN that I can get from the Lambda console or from the CLI. And then there's the asynchronous task. The asynchronous task is what we call an activity task. And it's similar if you use a simple workflow in the past. It's on the service that we have. It's an activity that is polled by workers. So you can create an activity that can be, for example, maybe I want to have people rate how nice a picture is from 1 to 10, something that computers start to be doing, but probably in a different way. I can create an activity, and then when I create an activity, this will be polled by a pool of resources. Can be containers on EC2, can be resources running in another data center, and there's an API for doing the polling. So basically, you register and create the activity task. Then whenever the code of the activity is running, you just poll for a task. And if there is a task to be done, we will give the input state to this task. Then the code can run in your data center on an EC2 instance whenever you want. And then you have an API to report the success or the failure of this activity. And if this activity is long running, maybe it takes hours or days, we also provide an heartbeat API so that you can say the activity is still running, everything is okay. Because if we see that you don't report the heartbeat for some time, we can think that something is not running well, is outside of our control. The activity is running maybe in your data center, and we will reschedule the same activity with another poller task. This is the Amazon state language. So as I said, it's an open source specification that goes through all the things that I mentioned and with great detail and more information. So I strongly suggest to have a look at it. And as I said, it's open source. So if you want to, if you are thinking of building something similar or you need similar concept, you can get it from here because it's a completely open source documentation that we provide. The state machine can integrate with other AWS services. So you can create state machine and activities with CloudFormation. So you can have your SEM template or CloudFormation template that describes also the flow of the state machine. You can also execute a state machine from the API gateway. But this is an asynchronous operation because the state machine is not synchronous. So if you invoke the execution, the feedback of the API will only be, okay, the state machine execution has started. You can't get a result. But this is useful if you have a complex business process. It really depends. You can directly go from the API gateway to invoke the execution of a state machine, or you can call a Lambda function, and then the Lambda function can do different things. Start the execution of the state machine and then maybe give back some graphics or some information in a more formatted way. Usually the example that I give here is if you build an e-commerce website, maybe most of your website is built with Lambda API if you go serverless. But then if you purchase something, then you need to start a workflow because the purchase operation is much more complex. You need to start a workflow that will look effectively, the payment is correct, the availability of the product is correct. I start the delivery, and maybe this workflow can follow all the delivery of the item that is shipped to the customer. So it can run for a few days and can send the emails with the updates. Okay, your status of the delivery is shipped in this warehouse, is going to be delivered tomorrow. So you can really build a business process in this way. And you can either start directly from the API gateway or use a Lambda function in between. It's also integrated with CloudWatch events, so you can use CloudWatch events to trigger state machines or schedule state machines. So if you remember in my previous session, I said that Lambda function can replace those scripts that we all do in our data centers to clean up the stuff or take backups. If it's something more complex, and we will see an example, you can trigger a state machine that can be much more robust and then can launch multiple Lambda functions to apply the task, retry the task, get the result, and work in a more robust way. You can log the calls to CloudTrail, so if you have any compliance, this is very useful. And mostly you can start state machine from a Lambda function. That's the normal use case that we see. The console will automatically write design the visual workflow from the JSON that you provide. And this is what you would do for the images image recognition that we were talking to today. I think I also have an example afterwards, but the day you start, then you have a first task that is extracting the metadata from the pictures that you upload. Then you can have a choice if the image format, so you have a Lambda function that checks the type of the images. If it's supported, you go on, otherwise you give an error that is not supported, so you fail with a state fail and not supported image type. Otherwise, you store the image, you launch Amazon recognition in parallel with the generation of thumbnails, because these two things can happen in parallel and speed up the process. Then the generation of thumbnails ends. You also take the tags found by recognition and you store them, for example, in DynamoDB. When both the parallel branch ends, then the whole process will end correctly. If you have an error, you will intercept, and the two things happening in parallel will not end. So if you have multiple parallel execution, all the parallel execution must end correctly. This is an example of how you can use step functions to do a human approval task. And basically, you can have, for example, CloudWatch that can schedule a Lambda function. The Lambda function can, on one side, create an activity task here, and on one side, send an email. The email goes to the user that has some decision to take. He can approve or not approve something. The two links, succeed or fail, go to the API gateway, and the API gateway can directly send the task success or task failure. You remember the two of the APIs for activities, back to step function, and this will close the circle. So in this way, you can give this task will succeed or not, and then in the state of your state machine, you can have different branch. If the state fails, this has not been approved, so maybe I take some action. If it has been approved, then I go in another branch and do other actions. And you have up to 1 year between when you send the email and when you have to take the decision. So it's much more flexible than other configuration. This is the same as before, so the image recognition. This is the architecture that you saw today in a couple of presentations for extracting the information. This is the state machine diagram. And I don't know, to me, the diagram on the left is much easier to understand than the one on the right. The one on the right is really architectural. It's telling you how all the building blocks, S3, DynamoDB are flowing. This one is much more clear on the flow of the operation. It's telling me that this either works or fails, and what are the different states that the data will go through. I didn't mention, but all those links at the bottom is because there are articles that you can then find and see in more detail. This is an EBS Snapshot Management state machine. So if you use EBS, the Elastic Block Storage, which is the storage that you can connect to EC2 instances, you need to have some procedure to take snapshots, the equivalent of backups. And this is a snapshot management state machine that will do 4 things. First, we'll tag the snapshot with your information. Then we'll count the snapshots. It will copy, so we go again in the multi-region scenario from the previous session, the snapshot in another region. And then it delete the expired snapshot, so that you only keep, for example, 5, 10 snapshots for every volume, and not more than a number that you specify. So in the first region, this starts. It will replicate in the other region. In the other region, when the snapshot is replicated, this triggers a CloudWatch events that can start the same state machine that will locally check and eventually delete the oldest snapshot, so that also in the target region you keep only the latest 5, 10 snapshots for every volume and not more than that. So this is quite a complex workflow to manage manually. You can do scripts to do that, but in this way it's very clean and the state is managed completely by the platform. And there's a nice article here. No, this is the GitHub repository, so that describes how to set up this environment. So let's see how this works live. So this is the AWS console. Step functions are in the application integration section. And we can get started. Here we have, you can author from scratch, similarly to Lambda. We have a couple of projects. We are going to add more that are tied to our tutorials. So if you want to invest some time, you can follow these projects. And we have a very few templates that are very basic, but gives you an idea of what you can build. So let's have a look at those templates. So the first one is the hello world. The same one that we saw before is the single state state machine that starts at hello worlds and then ends. Nothing interesting. Second one is the wait state. And the wait state is, we see the diagram here. So it's first starting a Lambda function, a task. And then there's a task at the end. And in the middle is waiting for some time in multiple ways. So here we have the same state. So we start at first state. And then there is the list of the states. So this is the first state. It's a task, it's a Lambda function. So typically this is the syntax of an ARN. So the function ID, account, and region. And when this task ends, the next state is wait using seconds. This is a name of a state. And this is the state. And this is a state of type wait. And it will wait for 10 seconds. And then the next state is wait using timestamp that, as you can imagine, is similar to the previous one, but instead of having seconds, has a full timestamp with this syntax. So it will wait exactly for this moment in time, and then it will go to the next state. And these two states here are using the fact that you can manipulate the state that is passed from one state to another. So, and we're using JSON path. So JSON path, I'm not entering into details, but basically dollar means the root of the JSON document, and then you can navigate the single components of the JSON document. So basically here we're looking for an expiry date in the state. If there is an expiry date in the state, we use that as a timestamp path so a timestamp to wait for before moving on. And the second one is doing is looking for a JSON property, this is expiry seconds, and then it will wait for those seconds, so this is a number, not a date, before going on to the next state. So the idea here is you can wait for a certain amount of duration or for an explicit moment in time, and this can be hardly put inside the state machine or can be part of the input-output that one state is passing to the next state, so quite flexible. And then the final state is running a Lambda function and is ending. This template is the retry failure, and this is very important if you have a Lambda function that is doing something mission critical, maybe is manipulating money in some way, and you want to be sure that if there is an error, you can catch it and maybe retry. It's also useful if maybe the Lambda function is calling an API that you don't control. So maybe you can get failures, you can get bottlenecks, something that you can manage, but you need to manage on your side. And this is how you do that. So basically, you have a task that is, in this case, a Lambda function, and then you can have a retry section. And the retry section can catch errors. So there are different ways you can report errors, and Lambda is integrated with that. So if you get a custom error, that means an error that you declare in the code, then you wait after 1 second. You do 2 attempts, so you try for 2 further times. And you have a backoff rate of 2. So the backoff rate is something that we use a lot in AWS and in Amazon. And the idea is that if the #1 reason when you don't get when you get an error from an API is because there's too much load, and the backoff rate will multiply the interval second by the backoff rate, so that the first time you retry after 1 second, the second time you multiply by 2, so you retry after 2 seconds. If this would go on, you would retry after 4, 8 seconds, 16 seconds, and this helps spread a peak of requests into a large amount of time. So it's something that we do a lot, especially on the APIs that we don't expect customer to call us too much. So maybe creating a VPC shouldn't be an API that a customer is calling 1,000 times per second. So if you start to do this, then we try to slow you down and try to understand, maybe then you can understand what you're doing. The second one is getting these other errors. The states error here are error managed by the state machine platform. So if the task failed, then you retry after 30 seconds, only for 2 times, again with a backoff rate of 2. So after 30 seconds, and then after 60 seconds, I retry. If I get any other error from the state machine platform, then I retry after 5 seconds for 5 times, and every time I have a backoff rate of 2. So 5 seconds, 10 seconds, 20 seconds, and so on. So this is how you can really fine-grain how you catch the error and retry the function. So if you're calling a third-party API that you don't control and you get an error or a very slow or a timeout, then you can use this to catch that and retry. We will see a few examples afterwards. Parallel is the type of state that has 2 or more branches. There's no limit in the number of branches, if not in the length of the document. So, and it's basically you start at this parallel state that is type parallel. When all the parallel branch inside this state ends correctly, then you go to the final state. And inside those branches, you can have, again, a list of state. And each one has a starting state. So this starts at wait 20 seconds, and this is, of course, a 20-second wait. The second branch here is a pass state, so it's not doing anything, but then it's passing to another wait state that will wait for 10 seconds. So if we run this, this will end after 10 seconds plus a few milliseconds for the pass state, and this will wait 20 seconds, then both ends, and then the final state will be triggered. This is something that is very basic when you look at here, but if you need to build that reliable in software in a distributed architecture, it's not so easy to implement. Catch failure is similar to retry, but it adds the possibility to catch an error, and depending on the error, go to different states. So it's not really visible, but the idea here is that I have an hello word state, and then depending on the error, I go to different tasks. So the custom error fallback will manage a certain error. This type, the reserved type fallback, will manage a different error, and then I have a catch all that will catch all the other errors. So here, again, I start at the hello world state, that is a task, and this task has a catch. And if the error is custom error, so some custom error that I explicitly generated in my code, then I go to the next state, custom error fallback, and then those are states, error from the state machine, and then I have the 3 states that I want to the flow go depending on the error that I got. And if there is no error, this the first hello world will just end. So let me put it more visible here. So the first one, if there are no error, will just end. So the hello world can also end directly. And the final one is a pure choice. So it's similar to the catch, but the choice is depending on the value of the state that is passed. So you can get the output of, you have the first state that is doing something, and then next you have a choice state. The choice state will look in the output of the state. If there is inside the JSON document a foo object that is equal to 1, so in this case I'm using numeric equals, but there's also string comparison if you want, or greater than, greater equal, less than equal. If it's 1, then I go to first match state. If it's 2, I go to second match state. Otherwise, the default state is this one, and everything else goes there. So this is an example of a choice, not on an error, but on the value of the parameter. So let's try to build a very simple state machine, and let's go on with the example of this morning. So if you remember this morning, I was creating this very simple function that you give the name and you get hello, good morning. Now I want to build a little bit of workflow. So I want to validate the name. I want to be sure that the name is correct. So maybe in a business process, you validate the customer ID on your customer database or something complex. In my case, I just do some basic name validation. My name is valid and all the other names are not. So that's the validation that I'm going to implement. And then if the name is valid, I will greet the name. If the name is invalid, I will process with some other Lambda function an invalid name. And for example, you can send an email or give more information to the user. So how can we build this? So we need, in this case, I'm using Lambda functions, not activities. So I need 3 Lambda functions that I already created. So let's go on Lambda. Let's put name as filter, and we can see the 3 functions. So we have greet name is the final one in the workflow. So we have validate name. So here I'm not expecting an input from an API gateway. So I'm expecting a very basic object. So the event, as in my first example, should contain name. This is the list of valid name, Danilo, Daniel, and Danny. All other names are not valid, according to me. And this is how you can declare a custom error with the JavaScript syntax supported by state machine. There are infinite ways to declare custom errors in JavaScript. This is the way we suggest and works with state machines. And we have examples for other languages such as Java, JavaScript, Python, and so on, C#. So what I do here, I look if the event contains a name. If there is no name, I create the error name error, and the error can have a message, and I pass the message no name. If the name is not in the list of my valid names, then I create another error, still a name error, but I pass a message wrong name. And then if there are no errors, I terminate correctly, so null means no error, and then I pass the event without any manipulation. So this is an example of a state that is acting as a pass-through if everything works, otherwise it's rising an error. In case the name is valid, it's the same function as today, so slightly different, I think. So this is, no, sorry, this is the validate. Let me, usually the more you zoom, the more JavaScript fights back. So let's go to a valid, no, this is the validate, this is me, not JavaScript, I think. So let's go to the greet name, and the greet name will of course just take the name. Now I can easy my constraints because I expect that the error has been validated, but I say hello plus the name. If there is no name, I say hey, and then I just say the greeting. Technically, this check could be avoided because I added the validation to the state machine, but this depends on the robustness that you want to put into your process. And then if the name is invalid, I just look into the error, and there is a standard way where you get the message that you pass to the error, you get it into the cause of the event. And the cause can be a wrong name or a no name, and then I send back this message. I don't know how to greet this name because it's not a supported name, or please, I need a name, give me at least a name to greet, or there is an unknown error. So those are very simple functions. And the idea is that with state machine, you can take a larger function and easily the constraints, the checks, and build smaller building blocks of code. The smaller the code, the easier it is to manage and to extend and to add functionality. So that's the agility that you get from this kind of approach. This is, of course, an extremization now, but it gives you the idea. So, OK, we have the three functions. We can go back on the state machine and start and create our state machine from scratch. Let's call it DevDays, DevDays Stockholm. I already created a role, but the first time it will automatically create a role to give the permission to the state machine to invoke the Lambda functions, because otherwise, if you don't give permissions by default, state functions can interact with other services. And here I can start writing the code. Luckily enough, I already have a bare-bone state machine here. So I copy here. We just refresh the wizard workflow, and we see that the wizard workflow is what I wanted to build. So I have a start, a validate name, invalid name, and greet name. And here I have it, but if you see, for example, for validate name, I have a task, but there's no resource. But if I click here, the console will automatically show me the available functions in my region, and this is the validate name. So I can add this. This is the ARN. Then the second task is invalid name, and here I have the process invalid names. Okay. And then the greet name, I have the greet name here. And now I link to the three states. And if we see, the first one is a task that will catch an error, and if the error is a name error, we'll call invalid name. Otherwise, we'll pass to the next greet name. So this is an example of how you can build this. Now I can create the state machine. The state machine, then you can copy to new and create a different version, or you can edit now. This was not possible at the beginning. Now you can edit. And now you can start execution. And the execution of a state machine needs an input document, a JSON document. So let's give a valid name to start the first execution of the state machine. So Danilo. And you see, this is starting. I don't know why it wants to zoom. Validate name is in execution, and now it's going to greet name because green means that the state is executed or in execution, and then it ended and succeeded. I can see the input was name Danilo, and the output was, of course, hello Danilo. But if I go here, I can see all the steps with the timing, how the function were scheduled. I can see the Lambda function, the logs of each function, so of each step in the state transition. And if something goes wrong, you can really dive deep here. You can also click here on the state, and then you get the state detail. So this state has this input and this output, because no error was raised, and you remember it was not changing the state. The second step was getting this input and generating this output. So here, visually, you can really navigate and see anything that is happening. And let's try a new execution. And let's give a wrong name. So let's write Danilo with the H. You see that now validate name is executed. Now this is going on the invalid name branch. The time and the speed of the state machine should not be, it's not exactly the same that you see in the console, because the console there's some like polling and it's designed to be reliable, but it's much faster than that. In a few milliseconds, everything was executed. And I get the input was Danilo, and the output of this was I don't know how to greet this name. And then I can click here, and I see that there was this input, and the error was, and the output was an error with the error message that wrong name. And just to do the final check, oops, we can do the final execution with no name. So I pass an empty JSON object, and it already ended, and it's please give me a name to greet. So, and if I click here, I can see that the input was the error and the output. Now there was no name and not wrong name in the error message, so the output was give me a name to greet. And again, here I have all the details. So if I click here, I can see all the logs. I don't think I was logging too much from those functions, so I'm not sure if it makes sense. So this is how you can build a state machine. And if you want to add an activity, it's as I said, it's a strange concept, but just to give you an idea, I'm using the CLI here. So let's clear. So the AWS CLI that runs anywhere because it's written in Python. You have AWS, then you Step Functions, and then I have activated autocomplete, so it will automatically show all the possible subcommands. And this maps, in this case, one-to-one to the API. So if you use Python, Java, whatever language, you have the same methods or functions in your language that you can use. And here you have create activity and delete activity that can create an activity. It's just a name, because there's no Lambda function in this case. Then you have the get activity task here. The get activity task means that this is the API that you use to poll. So if you want, for example, to have a human validation or an advanced machine learning validation on the name, instead of having a Lambda function, you can have some code running on HC2 or on-premise or in a container, whatever you want, that will continuously call this maybe every 30 seconds, this API, and say, hey, there's something to do for the activity validate name. If there's something to do, this API will say, yes, there's actually this task that must be executed. This is the input state, so name Danilo, name or no name provided. It will be the state that was in the transition of the state machine. And then I can start any complex business process I want that can go for hours, days. I have here the send task heartbeat that can be used. You can configure an heartbeat, for example, every 5 minutes, every hour, depends on how often you want to be sure. And this will tell that the activity is running. If we don't get the heartbeat in time, then we assume the activity failed, and we will reschedule this automatically to another poller. And then you can call send task failure or send task success to report the end of the task. So, okay, this is a valid name, or no, this is an horrible name. I will never greet this name because it's something I don't like. So in this way, you can execute code outside of Lambda, of serverless, but it can be used also to easily integrate this with a workflow that you already have. So maybe you have, I don't know, a risk evaluation process in finance. You just need to pass the input of this command to the process, eventually add an heartbeat that can be a parallel process that checks that everything works. And then when the process ends, you get the output from your current application, you remap it into the syntax, the JSON syntax that you expect, and then you throw the failure or success. So it's very easy to integrate an application that you already have as an activity task for a state machine. Any question here? See that we're getting all a little bit tired. So We saw how it works live with a very basic example, how you can extend it. Let's see a few use cases that maybe makes this a little bit more understandable. So the first one is Coca-Cola. All these case studies are taken from our reInvent in Vegas, so they are from the beginning of December. So they have this application. I think this is US only, but I never saw it in Europe, where you can pay at a vending machine, at a Coca-Cola vending machine with an application. And basically, if you buy Coca-Cola, you get some tokens that then you can spend for having free drinks. And they were having this problem that sometimes, even if the customer was maybe buying like 3 drinks and he was paying cash, then every 3 drinks you should get a free drink. He was trying to get the free drink and it was giving an error. There was no credit. So there was a problem with the credit being out of sync. And this was, of course, giving a better user experience because you expected to be able to do that. They did some analytics and then they realized that the old architecture was updating the consumer database, but the consumer database, that is a legacy application that they have on-premise, was simply slower, not fast enough to catch up with the speed of something running serverless in the cloud. So now what they do is that when there is an update, so basically what was happening is that they were triggering a serverless saying, okay, the consumer database has been updated, but then this new value was taken and reported immediately, but it was still sometimes the old value because it was too fast. So now they start using SNS, a step function that will wait for 90 seconds. So, and then after 90 seconds, we read the state and write the state in the new modern fast application that is used by the backend of the mobile app. So it's just a simple trick, but you can imagine that solving this normally would have been quite complex. But in this way, it was very quick for them to fix, and now they're looking at maybe better solution for long term. This is Thomson Reuters. And Thomson Reuters, they sell basically content and information to their customers, at least most of it, because Thomson Reuters is quite a diversified company. And one part of their company, they're selling videos. And the value of the information that they provide is in the speed at which they can give the video to the customer. Problem is that they need to transcode 350 clips per day in 14 different formats, because anybody can use a different device. They use FFmpeg, so we have our own managed transcoding service, but they use FFmpeg, okay. And normally with FFmpeg, the transcoding time is the same as the length of the video. So that means that if you have a 30 minutes video, it takes at least 30 minutes, even if you run all the transcoding in parallel before you can give the video to the customer. And if this financial information is probably not what you want to do. So they, by themselves, they created this solution. So they use FFmpeg to look for all the keyframes in the video. The keyframes are the frames that in the video encoding are provided with complete resolution. Normally, most video encodings, they have keyframes, and then they have the delta from the keyframes for like half a second, 1 second, and then they have another keyframes. So they look for all the keyframes, and this is a very fast operation with FFmpeg because there's very little I/O. Then they split the source video at all the keyframes so that they have very small segments, like half a second on average. And then they process all those small segments in parallel with Lambda functions. So they prepare the split, then they perform the split, and then they prepare the rendering of all these small parts. And from 20 minutes, they go to roughly 2 minutes. And mostly it's the time of looking for the keyframes and then assembling everything back again. So if we look a little bit better, so they prepare the split, and then when the split is completed, they go to the split prepared state. Then they perform the split, and then they enter to split performed. And then they decided to not manage all the Lambda execution inside the activity here, but since the split performed will write roughly 1,000 or 2,000 or thousands of small files on S3, each of these small files will trigger a Lambda function that will process this file. So they don't need to coordinate this here. And then they just wait for the results to finish. So all those thousands of Lambda functions running in parallel will write their output, and they have a loop where they wait for all the results. When they count the results, if all the Lambda function terminated and they have an exact number of output segments as they expect, then they go to the segments complete state, and then they merge everything and finish, and then they have the video in parallel. So it's quite a strange setup. By the way, inside Lambda, if you remember, you only have memory and a relatively small /tmp. It's 512 megabytes, and the space of the /tmp doesn't change. So they use some advanced features of our CLI that are very handy with Lambda. So basically, you can stream the output of FFmpeg straight to S3 without storing the intermediate file inside the Lambda function. And basically, the copy operation, so AWS S3 copy, as the input and the output, and both the input and the output can be replaced by dash, that in Unix means this is standard input or standard output. So this means do the encoding of the small segment, send the output to the AWS CLI that will take this output and write the output into this object on S3. And there's no writing on disk in the middle. And you can use also the same to give the input. So you can use the same syntax. So you put the dash afterwards, and you can have the input bucket, and you can have everything happening in memory. So no storing of the data. So that's why the 3 gigabytes are important, because the 3 gigabytes of memory for Lambda function enable activities like this that don't need disk but are memory intensive. And so as I said, when they wait for results, we'll just wait for the S3 triggering thousands of functions. And then they have created a loop. And the loop is, so let's see the state machine, how it works. So they have an init operation. They prepare the split. And then they do all the steps that we saw together. And if we have a look, we can notice that it's always the same Lambda function. And this is quite strange, because you do completely different things, but you always have the same Lambda functions. So this is an architectural choice. But basically, if you look here, there's this result path and result. And this is a way to modify the state that is passed from one state to the next state. So basically, here they're saying, take the input object and add an operation property that contains prepare split. So the operation is prepare split. So this Lambda function will look in the event for an operation, and depending on the operation, will execute different part of its code base. So the prepare split will prepare the split. Operation is perform split, and then you have the execution of the same Lambda function. The Lambda function in the event will find the operation perform split, and it will do the split. That's why we have this prepare split and split prepared. And then you have perform sleep and then sleep performed, because one step is creating the input object with the current operation, and the next one is executing the code on Lambda. And this goes on. And then they wait the final wait is using the same function again, but if we see, basically, you go to the wait result, and then to the wait result, if we go back here to the wait for result, you go with poll status submitted. So we go here, wait for result, poll status submitted, next state, loop wait using seconds. Loop wait using seconds, I wait 3 seconds, and then I run the Lambda function to count the number of objects. Then I go back to wait for results, and wait for results will look if the poll status is complete, progressing, or progressing. Submitted will never, probably is progressing, and then you go there, wait 3 seconds, check again, and then you go here and it's progressing. When this function will report the state complete, you go to segment complete state, where I say operation to concat, and then Lambda function will be executed with operation concat and will be terminating. In the state, there are other information and we don't see, but like the number of segments and information to process. So this is quite a strange setup to me, but it's very robust and helps them do all those transcoding at speed. And this is, I think, the final example that I want to talk about. it's frame.io, still in the video area. So they do video review and collaboration. And when they do the transcoding, they sometimes think it's better to use Lambda to do the transcoding, especially if the file is smaller. But if the file is big, they just use ECS, our Elastic Container Service. So they run a container that doesn't have the 5 minutes timeout. So they were doing this with lots of complex code. And then they design a state machine. They have an encoder decider that will decide, depending on the characteristics of the file, if they want to run on ECS or on Lambda. If they run on Lambda, then they can either terminate correctly or fail. If they run on ECS, they wait a few seconds, see if the task is being executed and completed. Otherwise, they have a couple of loops here. I will enter into that. And then when the task completes, they have a success or a failure. And then, of course, they can reuse all the code here. This is independent from the fact that they're using Lambda or ECS. So if we look at the code, we see that the decider is looking at some information that is provided when you start the machine. That is the asset size and the asset duration in milliseconds. So if it's less than 2 gigabytes and less than 10 seconds, then we go to run the Lambda encoder. Otherwise, we go to run ECS encoder. And we also realized that sometimes the fact that we use default as keyword here is not very readable. Maybe we should have called it else. So this was something, maybe we can create an alias. And then when the ECS encoder has a retry here, and we noticed that they were retrying every 5 seconds for an hour. So there are 720 attempts every 5 seconds. And at first, we didn't understand why they were doing this with ECS. But the reason they told us is that they have a cluster that is in autoscaling. And sometimes they fill up all the resources. So the container scheduler can find any instance that has the resources to run the container. But the autoscaling in a few minutes normally is going up and down and it will grow. So they added this, and then they basically, if there is the error is no resource in cluster, they will just loop here until the cluster will autoscale. And usually it takes like 5-10 minutes. But they added 1 hour just to be sure. And this is a way to retry until the autoscaling cluster of the container service is growing. If you were at the Fairgate presentation today, so we talk about Fairgate, it's a new container scheduler that we launched where you don't need to manage the cluster. This will not happen because in that case, we manage the cluster and you always get the resources for containers. And then when you finish this, there's the normal termination. And this here is that at the end, they fire CloudWatch events to notify if everything works or not, so that they can fire other logic, other state machine with these events. So these were a few examples, not probably the most advanced use cases, but I think very easy examples where you can very easily connect to. And here we have a few getting started guides with the example of the image recognition and the snapshots and others that are going to be added. And if you like something of these step functions, if you are planning to use them, please share on Twitter with this hashtag step functions. It's something that the product team is really interested to, and it's something a good way we're monitoring the use cases. In one of the presentations we did at reInvent, we said that this is one of those horizontal technologies that you create, you give to customers, and then they do completely the opposite of what you were expecting when you design it, like the else default word that is used differently. So we're really looking forward to get feedback and see what can be done with this platform. Thank you. Of course, I'm happy to take a few questions. And otherwise, since it's quite late, again, you know how to contact me. And I hope you enjoyed the day. It was quite a dense day, I think. But this is part of the feedback you have to provide if you prefer a different approach. We really try to put everything we wanted to could be of interest for you here in this event. Thank you.